Deep in space, a city of 1,000 galaxies hides secrets that defy physics. This is the Coma Cluster, and its mysteries are rewriting the rules of our universe. By the end of this journey, you will have explored 25 of its most baffling phenomena, each one a direct challenge to our current science. We will confront missing matter that should not be gone and witness galaxies that behave in impossible ways. What truly governs the chaotic heart of this cosmic metropolis? The first mystery strikes at the very heart of what we think we know about the cosmos. Astronomers have discovered a staggering amount of ordinary matter has simply vanished from the Coma Cluster. This is not the dark matter enigma, but something more immediate and just as puzzling. It is called the missing-baryon problem. Baryons are the particles that make up everything we can see and touch, from stars and planets to the very air we breathe. In a cluster as massive as Coma, models predict there should be an enormous reservoir of this normal matter, floating as superheated gas in the vast spaces between the galaxies. This intracluster-medium should glow fiercely in X-ray light. Yet when scientists point their most powerful X-ray telescopes at the cluster, the signal is far weaker than it should be. A colossal portion of the expected baryonic matter is not there. It is a deficit so large it cannot be explained by measurement error. Where did it all go? The leading suspect is a theorized, elusive structure known as the warm-hot intergalactic medium, often called the WIM. This is thought to be a cosmic web of faint, diffuse gas filaments, warmed to temperatures between 100,000 and 10 million degrees. It is notoriously difficult to detect because it is so spread out and not dense enough to emit strong X-rays. Some of the missing baryons from Coma might be hiding in this faint, web-like structure surrounding the cluster, but confirming this is a monumental challenge. It means a fundamental component of the universe's ordinary building blocks is currently unaccounted for in one of its largest structures. If we cannot find the normal matter, how can we ever hope to understand the rest? This missing matter is just the first layer of a deeper, more profound enigma. Holding the entire cluster together is a vast, invisible scaffold of dark matter. We call these structures dark matter halos, and they are the true skeleton of the cosmos. Without them, the immense gravity of the Coma Cluster's 1,000 galaxies would not be enough to prevent everything from flying apart. These halos are not solid objects, but enormous, diffuse clouds of an unknown substance that permeates and surrounds each galaxy, binding them into a single titanic structure. We cannot see dark matter directly as it does not emit, absorb, or reflect light. Its presence is felt only through its immense gravitational pull. To map these invisible halos in Coma, astronomers use a cosmic trick of light called gravitational lensing. The tremendous mass of the cluster, dominated by its dark matter, warps the fabric of space-time around it. This warping acts like a giant, irregular lens, bending and distorting the light from even more distant galaxies far behind the cluster. By meticulously studying the patterns of these distorted background galaxies, scientists can create a detailed mass map, revealing the precise distribution of the cluster's total gravity, and by extension, the shape and density of its dark matter halo. What these maps reveal is deeply puzzling. The distribution of dark matter does not perfectly match what our best supercomputer simulations predict. There is a persistent tension known as the cusp versus core problem. Simulations consistently show that dark matter halos should have a cusp, a sharp, dense peak of dark matter at the very center of a galaxy. Yet observations, including those of galaxies within Coma, often suggest these halos have a core, a more spread out, uniform distribution at their heart. It is as if something is preventing the dark matter from clumping together as tightly as the laws of gravity demand. This discrepancy forces a radical question. Could dark matter particles be interacting with each other or with ordinary matter in ways we never anticipated? Perhaps they collide or scatter, generating a kind of pressure that smooths out the central cusp into a gentle core. The intense environment of the coma cluster, with its frequent galactic collisions and turbulent gas, might be the perfect laboratory to see these subtle effects in action. If dark matter has any properties beyond simple gravity, this chaotic metropolis could be where its true nature is finally exposed. The ghostly heart of the coma cluster holds a paradox of its own. At the center of this cosmic city lies NGC 4889, a colossal elliptical galaxy that defies simple classification. While it appears as a brilliant, dominant beacon, its outer regions tell a different story. They are astonishingly faint and diffuse, spreading starlight so thinly that the galaxy seems almost transparent against the blackness of space. This makes NGC 4889 a prime example of an ultra-diffuse galaxy, but one of unimaginable scale. How can something so massive be so ghostly? Its stellar population is strangely sparse for its immense size, as if the galaxy never managed to form the trillions of stars its sheer bulk should have allowed. Even more puzzling is the monster it harbors within. Nestled in its core is one of the most massive black holes ever discovered, a gravitational titan with a mass billions of times that of our Sun. This presents a cosmic contradiction. A supermassive black hole of that magnitude typically sits at the center of a densely packed, star-rich galaxy, having grown fat on a constant diet of gas and stars. Yet here it resides in a galaxy whose outer halo is wispy and underpopulated. So what happened? Astronomers have two leading theories, each a tale of cosmic violence. The first suggests NGC 4889 might be a failed giant. It may have formed in a region of space that was strangely devoid of the cold gas needed to birth new stars, leaving it massive in dark matter but star-poor. The second, and perhaps more compelling, theory points to the brutal environment of the cluster itself. Over billions of years, as NGC 4889 plowed through the dense intracluster-medium at the cluster's heart, the immense pressure could have violently stripped away its outer layers of gas and stars. This process, called ram pressure stripping, might have left the galaxy's dense core and central black hole intact while scouring away its diffuse outer halo, creating the ghostly giant we see today. It is a reminder that in the coma cluster, even the mightiest structures are not immune to the relentless forces of their chaotic home. But the violence that shapes galaxies can leave even larger scars. Far out on the fringes of the coma cluster, astronomers have detected a colossal, faint arc of radio light. This is the coma cluster's radio relic, a structure so vast it defies easy comprehension. Stretching across millions of light-years, this ghostly bow is not made of stars or glowing gas. Instead, it is a testament to pure, raw energy. The relic emits a specific type of radiation called synchrotron emission. This happens when electrons, accelerated to nearly the speed of light, spiral around magnetic field lines in the thin plasma that fills the space between galaxies. The process creates a faint radio glow, painting a map of invisible forces on a cosmic scale. The sheer size and brightness of this relic point to a cataclysmic event in the cluster's past. The leading theory is that it is a fossil shock wave. Billions of years ago, the coma cluster likely experienced a monumental collision, merging with another massive group of galaxies. The titanic gravitational forces of that merger would have sent a tsunami of energy rippling through the cluster's intergalactic plasma at thousands of kilometers per second. Think of it as a sonic boom, but on a scale where the sound travels through a superheated, magnetized gas across the entire universe. This shock wave is the prime suspect for creating the relic. As it plowed through the cluster's outskirts, it would have acted like a natural particle accelerator, giving electrons a tremendous boost of energy and amplifying the local magnetic fields. Yet the mystery deepens when we ask how these electrons are still glowing so brightly today. A shock wave that passed through billions of years ago should have left behind only fading cooled particles. The fact that we still see such strong synchrotron emission means the electrons must have been reaccelerated, given a second cosmic kick to keep them radiating. How does this happen? One possibility is that turbulence in the wake of the ancient merger, or even newer, smaller collisions within the cluster, is continuously stirring the plasma, providing fresh energy. The radio relic, then, is not just a static monument to a past explosion, but a dynamic, living structure. It is a cosmic crime scene where the evidence is still active, challenging us to understand the ongoing, violent weather within this galactic city. While the radio relic marks a titanic shock wave, the cluster's interior holds a different kind of atmospheric disturbance. Scattered through the superheated gas between the galaxies are structures so sharp and defined they seem impossible. Scientists call them cold fronts. The name is a cosmic irony, for these are not cold by any earthly standard. The intracluster-medium is a searing plasma, with temperatures reaching tens of millions of degrees. A cold front here is merely a boundary where the gas on one side is slightly cooler, perhaps by a few million degrees, than the blistering gas on the other. What is truly baffling is the razor-sharp edge of these boundaries. In the chaotic, high-energy environment of the cluster, you would expect heat to diffuse rapidly, smoothing out any temperature differences almost instantly. It would be like pouring a cup of cold water into a boiling pot and expecting to see a distinct, lasting line between them. Yet these cold fronts persist for astonishing lengths of time, some for billions of years. They are like weather fronts in Earth's atmosphere, but etched into a sea of million-degree plasma on a galactic scale. So what could possibly create and maintain such a sharp divide? The leading hypothesis takes us back to the cluster's violent history of mergers. When a smaller group of galaxies plunges into the main cluster, it does not simply dissolve. Its own halo of hot gas is dragged along with it, like a dense bubble moving through a thinner fluid. As this subcluster gas moves through the even hotter intracluster medium of coma, it can create a sloshing motion. The cooler, denser gas from the infalling group sinks toward the cluster's center, while the hotter, lighter gas is displaced outward. The interface between these two masses can become a remarkably clean, sharp boundary, a cold front. But the mystery of its longevity remains. How does this temperature difference survive without being erased by conduction? This is where another invisible player might be at work: magnetic fields. Threaded throughout the intracluster plasma are vast, tangled magnetic fields. If these fields are aligned along the surface of a cold front, they could act as a powerful insulator. They might suppress the random motion of particles across the boundary, effectively preventing the hotter particles from rushing in to warm up the cooler zone. It would be like wrapping the cooler gas in a cosmic layer of magnetic insulation, preserving the front for eons. Each cold front, then, is a frozen snapshot of a past collision, a relic of ancient violence preserved by invisible magnetic forces. They are not static monuments, however. Observations suggest these fronts can be dynamic, slowly moving and evolving as the cluster's gas continues to churn. Studying them is like reading the weather report for a storm that began before our planet even formed. A storm whose atmospheric boundaries are still shaping the climate of 1,000 galaxies. The cluster's violent history has not only shaped its largest galaxies, but also scattered countless cosmic jewels in their wake. Orbiting the giant elliptical galaxies like NGC 4874 and NGC 4889 are vast swarms of globular clusters, dense spherical collections of hundreds of thousands of ancient stars. While most large galaxies have a few hundred of these clusters, the giants in coma are surrounded by thousands. This staggering overabundance is another signature of the cluster's chaotic past. Globular clusters are among the oldest known objects in the universe, fossilized relics from the first great wave of star formation. In a relatively quiet place like our own Milky Way, They formed in that early epoch and have orbited peacefully ever since. But in the Coma cluster, their story is far more dramatic. The leading theory for their incredible numbers points directly to the environment of the cluster itself. When galaxies collide and merge, as they have done countless times in Coma, they do not simply blend into a smooth soup of stars. The process is incredibly messy. The gravitational tides during these collisions can rip long streams of stars and gas from the smaller galaxies. Within these tidal streams, the dense knots of gas can collapse under their own gravity, triggering bursts of new star formation that create fresh globular clusters on the spot. It is a form of cosmic recycling where the destruction of galaxies gives birth to new, dense star clusters. Furthermore, the giant ellipticals at the cluster's heart act like gravitational vacuum cleaners. As smaller galaxies are pulled in and torn apart, their own ancient globular clusters are stripped away and captured, adding to the growing swarm around the central giants. This means the thousands of globular clusters we see today are a mixed population. Some are primordial relics from the dawn of time, while others are younger products of galactic violence. This overabundance serves as a direct archaeological record. By studying the ages, compositions, and motions of these clusters, astronomers can piece together the merger history of the entire cluster, tracing which galaxies were consumed and when. Each dense cluster of stars is a piece of evidence in the ongoing investigation of how this chaotic metropolis built itself up over billions of years. This faint cosmic glow is not a trick of the eye. Between the brilliant galaxies of the Coma cluster, a ghostly light permeates the darkness. It is called intracluster light, and it is the collective shine of countless stars that are no longer bound to any galaxy at all. They are cosmic orphans, adrift in the immense voids between galactic shores. This light is incredibly faint, 100 times dimmer than the darkest night sky we see from Earth, which makes it one of the most challenging phenomena to study. Yet it holds a direct record of the cluster's brutal past. The leading theory for its origin is one of galactic violence. When galaxies swing past each other in the dense cluster environment, or when they collide and merge, their immense gravitational forces act like tidal waves. These forces can rip stars right out of their galactic homes, flinging them into the intergalactic void. It is not a gentle process. Picture two vast crowds of people, each representing a galaxy passing very close together. The gravitational pull from each crowd would tug violently at the individuals on the edges, pulling some completely free and scattering them into the empty space between. Over billions of years, countless such interactions have filled the cluster with a sea of these lost stars. The puzzle for astronomers is not just confirming this theory, but quantifying it. Exactly how much of this faint light is there? Mapping its distribution is a monumental technical challenge. It requires extremely deep observations and sophisticated software to subtract the overwhelming glare from all the individual galaxies and the background sky. But the reward is a revolutionary new map. The pattern of this intracluster glow is not smooth or uniform. Instead, it traces faint, wispy streams and broad, diffuse clouds. These structures are the fossilized debris trails of ancient galactic collisions and close encounters. By meticulously charting this ghostly light, scientists can essentially rewind time. They can identify which galaxies interacted, estimate how long ago those events happened, and even gauge the violence of the encounters. Some of the light appears concentrated around the giant central galaxies, suggesting they have grown fat by cannibalizing their neighbors. Other streams stretch between galaxies, marking the paths of past gravitational dances. This faint glow, then, is more than just lost starlight. It is the cluster's memory, written in the most delicate ink imaginable. It tells a story of a history written not in peaceful growth, but in a relentless series of cosmic robberies and shattered homes. Even the thin air between galaxies carries the chemical signature of ancient explosions. The superheated gas filling the coma cluster is not just hydrogen and helium, the pristine elements forged in the Big Bang. It is laced with heavier atoms, iron, oxygen, silicon, the very elements that make up planets and life. This is the result of cosmic alchemy, where generations of stars lived and died, seeding their surroundings with the metals forged in their cores. Yet here lies the mystery. The distribution of these metals is not what anyone expected. In a system as chaotic and well-mixed as the coma cluster, where galaxies have been colliding and churning the gas for billions of years, you would expect the heavy elements to be spread fairly evenly, like stirring cream into coffee. But they are not. Advanced X-ray telescopes reveal a patchwork quilt of metal enrichment. Some vast regions of the intracluster-medium are surprisingly rich in iron, while adjacent zones are curiously poor. This anomalous pattern is a direct challenge to our understanding of how the cluster evolved. If supernova alone were responsible, their explosions should have created a more uniform sprinkle. So what created these chemical islands? The answer points to two powerful and perhaps competing galactic forces. The first is the sheer violence of the cluster's formation. When large galaxies merged, the colossal shock waves could have pushed pockets of metal-rich gas far out into the cluster, depositing them in specific locations rather than dispersing them. The second force is galactic winds. In the early universe, intense bursts of star formation and the furious activity around supermassive black holes can generate powerful outflows, like cosmic hurricanes blowing metal-enriched gas out of a galaxy and into the intergalactic void. But these winds are not infinitely powerful. In the dense heart of the coma cluster, the pressure from the surrounding hot gas might have stifled these outflows, preventing some galaxies from contributing their metals to the common pool. Meanwhile, galaxies on the cluster's outskirts, where the pressure is lower, could have blown their enriched gas farther and more freely. This creates a complex historical record, where the patchy metal map we see today is not just a list of ingredients but a timeline. It tells us which galaxies had the most dramatic star-forming bursts, which black holes were most active, and how effectively the cluster's own atmosphere suppressed the spread of these elements. It is a chemical fossil, revealing that the enrichment of this cosmic city was a messy stop-and-start process, far from the smooth stirring we once imagined. This chemical patchwork reveals a galaxy population that has been fundamentally shaped by its environment. Among the most striking features of the coma cluster is what astronomers call the red sequence. If you were to plot the galaxies in coma on a simple graph, with their brightness on one axis and their color on another, a fascinating pattern emerges. The spiral galaxies, with their active star formation, show up as a scattered blue cloud. But the elliptical galaxies, those smooth, football-shaped giants, align with near-perfect precision along a narrow diagonal line. This is the red sequence. The brighter the elliptical galaxy, the redder it appears. This tight correlation is a cosmic puzzle. Why does nature produce such a uniform population of galaxies, all following the same strict rule? The color red, in astronomical terms, is a sign of age and quiet. It tells us a galaxy is dominated by old, cool, red stars, with almost no young, hot, blue stars being born. The red sequence, therefore, is a lineup of galaxies where star formation has been comprehensively and permanently shut down. The mystery is how this process was enforced so uniformly across hundreds of galaxies in the cluster. What cosmic mechanism could so efficiently quench the fire of creation? The answer lies in the brutal reality of life in a dense cluster, and scientists point to a trio of relentless processes. The first is ram pressure stripping, which we've seen scouring galaxies of their gas. As a spiral galaxy falls into the cluster and plows through the superheated intracluster-medium, the external pressure acts like a torrential cosmic wind, violently blowing away the cold gas clouds needed to form new stars. The galaxy is left with its existing stars aging together, turning redder over time. The second process is known more colorfully as galaxy harassment. This isn't a single catastrophic collision, but a death by 1,000 gravitational cuts. In the crowded downtown of the cluster, galaxies are constantly zipping past each other at tremendous speeds. Each close encounter exerts a tidal pull, subtly stretching and distorting the galaxies. Over billions of years, this relentless gravitational jostling can disrupt a galaxy's orderly structure, stirring up its gas and preventing it from settling down to form stars. It can also strip away a galaxy's outer, gas-rich regions, leaving behind a denser, redder core. The third and perhaps most decisive force is AGN feedback. At the heart of most massive elliptical galaxies lies a supermassive black hole. When gas does manage to fall toward this black hole, it doesn't always vanish quietly. It can ignite, powering a brilliant active galactic nucleus. The energy unleashed from this core doesn't just create a beacon of light, it drives colossal winds and jets of particles that blast outward through the galaxy. This feedback acts like a powerful thermostat. If too much gas starts to cool and collapse to form stars, the resulting influx of fuel wakes the black hole, whose outburst then heats and disperses the very gas supply, shutting down star formation again. In the dense environment of coma, these three mechanisms, stripping, harassment, and feedback, work in concert like a perfectly coordinated suppression system. They ensure that once a galaxy enters the cluster's inner realm and joins the red sequence, its days of vibrant star-forming youth are over. The result is that striking, uniform line on the graph, a silent testament to the overwhelming power of a galaxy's address to dictate its entire life story. The red sequence is a galactic graveyard, but the process of joining it is a violent, individual drama. Each spiral galaxy that dares to enter the dense heart of the coma cluster faces a trial by fire, or more accurately, a trial by wind. As these star-forming islands plunge into the superheated sea of gas between galaxies, they encounter a force so powerful it can strip them of their very essence. This is ram pressure stripping, and it is the primary engine transforming vibrant spirals into the quiet, red ellipticals that dominate the cluster. The physics is brutally simple. The intracluster-medium, though incredibly thin by earthly standards, is moving relative to the incoming galaxy at speeds of thousands of kilometers per second. The dynamic pressure this creates is like standing in the blast of a cosmic hurricane. It acts directly on the galaxy's own reservoir of cold, dense gas, the raw fuel for future stars. This interstellar gas is loosely bound by the galaxy's own gravity, but the immense ram pressure can simply blow it away like smoke scattered by a strong gust. What remains is the galaxy's stellar skeleton, the population of existing stars that are too tightly bound to be easily removed. The galaxy's spiral arms, fed by that gas, fade and dissolve. Star formation grinds to a halt. This seems like a straightforward path to creating a red and dead elliptical galaxy, but the reality is far messier and more mysterious. The puzzle for astronomers is predicting the exact outcome. Why do some spirals transform completely into smooth, featureless ellipticals, while others become lenticular galaxies which are disc-shaped but lack spiral arms? And most intriguingly, why do a few manage to retain stubborn pockets of gas, defying the cluster's relentless wind? The answer lies in the details of the interaction, a complex balance of forces. The effectiveness of ram pressure stripping depends on three key factors: the density of the intracluster-medium the galaxy is plowing through, the speed at which the galaxy is moving, and most crucially, the orientation of the galaxy itself. A galaxy moving face-on into the wind, presenting its full disk like a sail, will experience the most extreme stripping. Its gas can be removed in a single, dramatic pass. A galaxy moving edge-on, like a knife cutting through the wind, might lose its outer layers more gradually, but there is another layer to this mystery. Galaxies are not simple, uniform disks of gas. Their interstellar medium is a turbulent, clumpy environment. dense molecular clouds where stars are born have much stronger self-gravity and can sometimes resist the stripping force, at least for a while. This can lead to a patchy, incomplete removal. We see this in galaxies within coma that show bizarre, one-sided tails of gas being ripped away, while their central regions still show faint signs of ongoing star formation. It is a galaxy caught in the act of transformation, with half its lifeblood already spilled into the void. Furthermore, a galaxy's own history matters. A spiral that enters the cluster with a particularly massive bulge of stars at its center has a stronger gravitational anchor, potentially holding onto its inner gas reserves longer. The stripping process is not always a swift death sentence. It can be a long, drawn-out quenching. The galaxy might first have its outer gas removed, truncating its star-forming disk and turning it into a lenticular. Then, over further orbits through the cluster, even the inner gas reserves may finally be scoured away, leaving only the red, dead elliptical core. This means that by looking at a gallery of galaxies in coma, some with long gas tails, some as smooth lenticulars, and some as perfect ellipticals, we are not looking at different types of objects but different frames in the same cosmic film. We are witnessing the step-by-step transformation of a galaxy's entire identity, forced upon it by the sheer brutality of its environment. The fate of a spiral in the coma cluster is not random. It is a predictable consequence of physics, yet each galaxy's individual struggle against the wind leaves a unique fingerprint on its final form. The brutal stripping of spiral galaxies is just one way the giants of coma grow. At the very center of this cosmic metropolis lies the colossal elliptical galaxy NGC 4874, a gravitational monarch that rules the cluster's core. But when astronomers peer into its brilliant heart, they find a stunning anomaly. NGC 4874 does not have a single, unified core. Instead, it appears to host multiple nuclei, several distinct knots of intense brightness embedded within its central glow. It is as if a giant eye has several pupils staring back at us. This bizarre structure presents an immediate mystery. Are we seeing genuine separate cores orbiting within the galaxy? Or is this merely a trick of perspective, a projection effect where smaller, unrelated galaxies in the background just happen to line up perfectly with NGC 4874 from our distant vantage point? The evidence strongly points to a far more dramatic reality. This is likely the aftermath of galactic cannibalism caught in the act. The dominant theory is that NGC 4874, sitting at the bottom of the cluster's immense gravitational well, has been actively consuming smaller galaxies that strayed too close. As these satellite galaxies are torn apart by the giant's tidal forces, their dense central cores packed with stars and often harboring their own supermassive black holes are remarkably resilient. They can survive the initial destruction and continue to orbit within the body of the larger galaxy for billions of years, like undigested pieces in a cosmic stomach. These orbiting nuclei are the fossilized evidence of past meals. Each one tells the story of a galaxy that once was, its identity stripped away until only its dense heart remains, forever circling the monster that consumed it. This process, called dynamical friction, will eventually cause these nuclei to spiral inward and merge with the primary core of NGC 4874, but that can take an astonishingly long time. So what we are witnessing is a snapshot of hierarchical growth in progress. The multiple cores are not a static feature, they are a temporary phase in the galaxy's evolution, a direct visualization of how the largest galaxies in the universe build their immense mass. They do not form in isolation, they grow by devouring their neighbors. This makes NGC 4874 a living archaeological site. By studying the motions, colors, and compositions of these multiple nuclei, astronomers can date the mergers. They can determine if the consumed galaxies were rich in gas and young stars or old and metal poor, piecing together the dietary history of this cosmic giant. The presence of multiple cores fundamentally changes our understanding of a galaxy's center. It suggests the core environment is not a quiet, settled place, but a dynamic arena where the remnants of past collisions continue to swirl. This also has profound implications for the supermassive black hole believed to lurk at NGC 4874's true center. If multiple black holes from the consumed galaxies are also orbiting within, they could eventually spiral together in a cataclysmic merger, releasing ripples in space-time known as gravitational waves. The multiple cores of NGC 4874 are therefore more than a curiosity. They are a direct testament to the predatory nature of galaxy growth in the densest environments, a reminder that the majestic giants we see today were built from the ruins of countless others. The cannibalistic giants at the cluster's heart do not just consume, they also expel. Astronomers have observed a startling phenomenon, entire galaxies being flung out of the coma cluster at incredible speeds. These are not slow, drifting departures, but violent ejections, with some galaxies racing away at thousands of kilometers per second, fast enough to potentially escape the cluster's immense gravitational pull forever. This process turns our understanding of a cluster as a bound system on its head. How can something as massive as a galaxy be thrown clear of the deepest gravitational well for millions of light years around? The mechanisms are as fascinating as they are brutal, rooted in the chaotic dance of gravitational physics. The primary suspect is a process known as a three-body interaction. Picture this scenario in the cluster's dense core: two massive galaxies, or perhaps a galaxy and a binary system of supermassive black holes, engage in a close gravitational encounter. As they swing past each other, they exchange energy. If a third, smaller galaxy happens to pass through this chaotic gravitational field at just the right moment, it can act like a ball in a cosmic pinball machine. The combined gravitational forces of the two larger bodies can give the smaller galaxy an enormous slingshot boost, transferring so much kinetic energy to it that it is catapulted outwards at a tremendous velocity. Another possibility leverages the cluster's overall gravity itself. A galaxy on a highly elliptical orbit that takes it diving perilously close to the cluster's central mass concentration can, under the right conditions, receive a gravitational kick that changes its orbit from a closed loop to an open escape trajectory. It is a celestial version of a slingshot maneuver used by space probes, but on an unimaginable scale. The true mystery lies not in confirming these mechanisms exist, but in predicting their outcomes. Which galaxies are destined to become cosmic exiles? The variables are immense. The precise speeds, masses, and angles of approach during these fleeting encounters determine everything. A galaxy ejected with just enough speed might eventually stall and fall back into the cluster in a billion years, while one given a more powerful kick could be lost to intercluster space forever. This raises a profound question about the fate of these ejected galaxies. What happens to a spiral or elliptical galaxy suddenly cast adrift in the vast, empty voids between clusters? Stripped of the dense intracluster medium that once harassed it, could a galaxy's star formation reignite if it still retains some internal gas? Or is it doomed to drift as a red and dead fossil, a ghost ship sailing an endless dark sea? These high-velocity ejections are more than a spectacular side effect. They are a vital part of the cluster's evolution, a way for it to shed mass and energy, and they create a population of isolated galaxies whose very existence challenges our models of where and how galaxies can live. The galaxy's fate is sealed not by the wind that strips it, but by a deeper internal silence. Even the most massive elliptical galaxies in the coma cluster, resting at the bottom of its immense gravitational well, suffer from a cosmic drought. They are surrounded by an unimaginable reservoir of hot gas, the intracluster-medium, yet they possess almost none of the cool, dense molecular gas required to birth new stars. This is the puzzling lack of cool gas, and it points directly to one of the most persistent mysteries in modern astrophysics, the cooling flow problem. The logic seems undeniable. The intracluster-medium in the heart of Coma is searingly hot, but it is also incredibly dense. According to the basic laws of thermodynamics, this dense, hot gas should be radiating away its energy in the form of X-rays at a ferocious rate. As it loses energy, it should cool down, and as it cools, it should naturally condense and flow inward, pulled by the immense gravity of the central galaxy, providing a steady rain of fresh, cold fuel for star formation. Computer models predicted that this cooling flow should be massive, capable of forming hundreds of new stars every year. But when astronomers look, they find almost none of this expected activity. The predicted downpour is not just a drizzle, it is virtually non-existent. Where did the rain go? The answer appears to be that something is constantly reheating the gas, preventing it from ever cooling enough to condense. It is as if a giant cosmic furnace is switched on just as the gas starts to chill, keeping the entire system in a simmering equilibrium. The prime suspect for this furnace is the supermassive black hole at the galaxy's core through a process called AGN feedback. When tiny amounts of gas do manage to cool and drift toward the center, they inevitably fall toward the black hole. This infall doesn't happen quietly. It can ignite the black hole's active galactic nucleus, launching powerful jets of relativistic particles and driving colossal bubbles of hot gas out into the surrounding medium. These jets and bubbles act like a giant stirring spoon and a heating element, dumping vast amounts of energy back into the intracluster gas, offsetting the cooling. It is a brilliant, self-regulating thermostat. Too much cooling triggers the black hole's outburst, which then shuts off the cooling supply. But AGN feedback might not be the only guard against the cold. Another subtle force could be at work: thermal conduction. In the hot, magnetized plasma of the intracluster medium, heat might be able to flow efficiently from the outer, hotter regions into the cooler central zones along magnetic field lines. This constant influx of external heat could be enough to stabilize the gas, preventing the runaway cooling that models predict. The true mystery is untangling which process dominates or if they work in concert. The evidence from Coma and other clusters shows cavities and ripples in the hot gas, the clear fingerprints of past AGN outbursts. Yet the precise balance of energy required to so perfectly quench the cooling flow is staggering to calculate. This lack of cool gas is not just an absence, it is an active state of suppression. It explains why these giant ellipticals, despite sitting in a sea of potential fuel, remain in the red sequence, their star-forming factories permanently closed. The cooling flow problem forces us to see galaxies not as isolated islands, but as the dynamic hearts of a vast, interconnected atmospheric system, where a monster in the core controls the climate for thousands of light years around. This pervasive radio glow is the cluster's own atmospheric noise. While the sharp radio relic marks a specific shock wave at the cluster's edge, the very center of Coma is filled with something far more diffuse and enigmatic: a giant radio halo. This is not a distinct object, but a vast fog-like emission that permeates the entire core region, blending seamlessly with the hot X-ray gas that fills the space between the central galaxies. Its existence tells us that the entire heart of the cluster is crackling with energy, but the source of that power is a major point of debate among scientists. The halo's radio light, like that of the relic, is synchrotron radiation, meaning it is produced by electrons spiraling at near light speed around magnetic fields. The sheer scale of the halo proves these high-energy electrons and the magnetic fields that guide them are everywhere in the cluster's core, not just at its outer edges. So how did these electrons get such a tremendous boost? How are they being fed so much energy across such a vast volume? Astronomers have three compelling theories, each pointing to a different kind of cosmic engine. The first theory points back to the cluster's violent merger history. The colossal shock waves generated during past collisions could have propagated throughout the entire central region, accelerating electrons uniformly and creating the halo in a single, ancient burst of energy. However, there is a timing problem with this idea. Electrons losing energy through synchrotron radiation have a limited lifespan. A shock from a merger that happened billions of years ago would have left behind only faded, cooled particles by now. The fact that we still see a bright halo today suggests the electrons must be receiving ongoing boosts. This leads to the second and currently favored theory, turbulent reacceleration. Imagine the core of the coma cluster not as a still pool, but as a constantly churning, bubbling cauldron. The motions of hundreds of galaxies, the sloshing of gas from past mergers, and the energy injected by black holes all create a state of magnetized turbulence. In this chaotic environment, electrons can get caught in these swirling eddies and receive multiple, smaller kicks of energy over time, like a pinball being bounced between bumpers. This process can continuously re-energize the electron population, keeping the radio halo shining brightly long after the initial merger shocks have faded. The third theory ventures into the realm of particle physics. It is called the hadronic model. Hadronic refers to particles like protons, which are much heavier than electrons. This model proposes that the intracluster medium is filled with a sea of cosmic ray protons, accelerated long ago by supernova or black holes. These protons are stable and can survive for billions of years. Occasionally, they collide with the much slower protons in the ambient hot gas. These proton-proton collisions create a shower of secondary particles, including the fast-moving electrons that then produce the radio emission we see. In this model, the radio halo is not powered by direct acceleration, but by the decay of an ancient reservoir of cosmic ray protons. Each theory paints a different picture of the cluster's inner workings. The turbulent model suggests a dynamic, weather-filled core where energy is constantly being recycled. The hadronic model suggests a quieter, more ancient energy source slowly leaking out over cosmic time. Observations are beginning to tilt the scales. The clear connection between the presence of radio halos and clusters that are undergoing mergers or are dynamically disturbed strongly supports the turbulent reacceleration idea. It suggests the halo is a living signature of the cluster's ongoing internal storm, a direct result of the chaotic weather that defines life in this crowded galactic city. The sea of red galaxies tells only part of the story. A deeper mystery lies in counting the survivors, the rare blue galaxies that still manage to form stars in this hostile place. Astronomers call this the blue fraction, and in the coma cluster it is shockingly low. Compared to the quieter outskirts of the universe or sparse galactic groups, where spirals glow with young blue stars, coma's population is overwhelmingly dominated by old, red ellipticals. This scarcity is the direct result of the quenching processes we have discussed, but the precise timeline of this cosmic shutdown is a major point of contention. Did star formation die a quick, violent death, or was it a slow, lingering end? Two competing narratives, each with its own evidence, seek to explain the fate of these blue galaxies. The first is rapid strangulation. In this scenario, when a galaxy first falls into the cluster's outskirts, its supply of fresh cosmic gas is cut off almost immediately. It can no longer accrete new fuel from the intergalactic medium, but it continues to burn through its existing internal reservoir. Star formation continues for a while, but like a car running on fumes, it gradually sputters out over perhaps a billion years. The galaxy's color would slowly transition from blue to yellow and finally to red. The second, more dramatic narrative is violent ram pressure stripping. This is not a slow starvation, but a sudden robbery. As the galaxy plunges into the cluster's dense core, the immense pressure of the intracluster medium violently blows away its cold gas in a single, catastrophic event. Star formation stops abruptly within perhaps only 100 million years, a blink of an eye in cosmic terms. The galaxy's blue spiral arms would fade quickly, leaving behind a redder, passive disk. So which process dominates? The evidence in coma suggests a messy combination, and specific galaxies tell the tale. Look at IC 3901, a spiral galaxy caught in the act of being stripped. It shows a classic, one-sided tale of gas being ripped away by ram pressure, a clear sign of violent, ongoing removal. Yet, intriguingly, its central regions still show pockets of star formation, suggesting the process is not yet complete. It is being strangled and robbed at the same time. Then there are the anemic spirals, galaxies that still have a disk structure but with faint, underdeveloped arms and very low star formation rates. These could be the victims of slow strangulation, galaxies that exhausted their fuel long ago and are now just fading quietly. The puzzle of the blue fraction is ultimately a question about a galaxy's journey. By mapping where the few remaining blue galaxies are located within coma, astronomers find they are almost exclusively in the cluster's outer regions or in infalling groups. It is as if the cluster core is a zone of absolute quenching, a place where the blue spark of creation is simply not permitted to survive. The low blue fraction, therefore, is not a static number. It is a dynamic measurement, a census that reveals the cluster's past and present efficiency at transforming vibrant spirals into red relics. Each rare blue galaxy we see is a holdout, a testament to a battle against impossible odds, and its very existence helps us clock how long the victory of the red sequence truly takes. The orientation of a galaxy might seem like a matter of chance, but in the coma cluster, even the direction a galaxy spins could be part of a larger, hidden order. Recent studies have begun to uncover a startling pattern. The spin axes of many galaxies within the cluster appear to be aligned with each other, and perhaps even with the vast cosmic filaments that feed the cluster itself. This is not what our standard models of cosmic evolution predict. In the picture of hierarchical formation, where galaxies grow through countless random mergers and collisions, you would expect their spins to be oriented in completely random directions, like leaves scattered by a chaotic wind. The emerging evidence of alignment suggests that the chaotic history of coma might have been imprinted with a subtle sense of direction from the very beginning. The statistical evidence for this is delicate and requires analyzing the shapes and rotations of hundreds of galaxies. Astronomers look for a preferred direction in how these galaxies are tilted relative to our line of sight and to the cluster's center. Finding a signal above the expected random noise is incredibly challenging, but several analyses point toward a correlation, particularly for the brighter, more massive galaxies. The implications of such an alignment are profound for cosmology. It suggests that the initial conditions that gave birth to these galaxies, the primordial swirls of dark matter and gas in the early universe, contained a coherent spin that was preserved or perhaps even amplified as the cluster assembled. Think of it like a vast cosmic weather system where the rotation of an entire galactic metropolis was seeded by the gentle spin of the infant universe. This alignment could be a fossil, a direct link back to the moment the cluster first began to condense out of the smooth expanse of the Big Bang. If the spins are also aligned with the large-scale filaments, it paints an even more interconnected picture. It would mean that the flow of gas along these cosmic highways, which fed the growth of the cluster, also imparted a specific angular momentum to the galaxies forming within it. The galaxies did not just fall into coma randomly, they were delivered with a specific spin, like water flowing into a drain with a consistent rotation. This challenges the idea that mergers alone dictate a galaxy's final state, pointing instead to the enduring influence of the universe's largest structures on the smallest details of galactic identity. The search for this alignment is a hunt for cosmic memory, a way to see if the universe's first whispers of order can still be heard in the chaotic roar of a mature galaxy cluster. If the alignment of galaxies hints at a hidden cosmic order, then the next mystery suggests entire cities might be missing from the map. Deep within the Coma cluster, astronomers are hunting for objects that should not exist, galaxies made almost entirely of dark matter. These theoretical dark galaxies would be vast halos of the invisible substance, holding together only a tiny, faint smattering of stars, or perhaps none at all. They are the ultimate cosmic ghosts. The idea itself is a profound puzzle. In a cluster as rich in gas and galaxies as Coma, where mergers and interactions constantly trigger star formation, how could an entire galaxy simply fail to light up? One compelling theory is that these are primordial failures. A dark galaxy might have formed very early in the universe from a small, dense knot of dark matter. But if this knot was in a region with an unusually low density of normal, baryonic matter, there simply would not have been enough gas to collapse and ignite significant star formation. It would be born dark, a shadowy island adrift in a sea of light. Another, more violent possibility is that they are the stripped remnants of a once normal galaxy. A small, low-mass spiral entering the cluster could have had all of its gas and even most of its stars torn away by tidal forces or ram pressure, leaving behind only its resilient dark matter halo and a handful of tightly bound stars. This dark skeleton would then orbit the cluster, nearly invisible. The challenge, of course, is finding something that emits almost no light. Astronomers have two main tools for this ghost hunt, and both rely on the dark matter's gravitational influence. The first is gravitational lensing. By creating exquisitely detailed mass maps of the cluster from the distortions of background galaxies, scientists can sometimes pinpoint compact regions of strong gravity that have no visible counterpart, no glowing galaxy at the lensing location. These empty lenses are prime dark galaxy candidates. The second method looks for disturbances in the hot gas. If a massive but invisible object were moving through the intracluster-medium, its gravity would create ripples or wakes in the plasma, similar to a ship moving through water. Detecting such a disturbance without a visible ship would be strong circumstantial evidence. While no definitive dark galaxy has been confirmed in Coma, several intriguing candidates have been identified in other clusters and in the field. Their potential existence forces us to reconsider the very definition of a galaxy. Must it be a collection of stars, or is the gravitational structure itself the true entity? If dark galaxies are real, they represent an entire population of cosmic objects we have been blind to, hidden components of the cluster's mass that have silently shaped its evolution from the shadows. The ghostly dark galaxies, if they exist, are just one way the cluster hides its true nature. To see the invisible forces at work, we must look at the weather map of this cosmic city. X-ray telescopes give us that map, revealing the temperature of the million-degree plasma between the galaxies. What we find is not a smooth, uniform ocean of heat, but a chaotic and patchy landscape of unexpected hot and cold spots. These temperature map anomalies are like the scars and fever charts of the cluster's violent life, each one a clue to a past trauma or an ongoing disturbance. The most striking features are vast regions that are significantly hotter or cooler than their surroundings, and they often appear in pairs or in complex, asymmetric patterns. These are not random fluctuations, they are the direct imprints of specific events. One of the clearest sources is past merger shocks. When two subclusters collided billions of years ago, the titanic impact sent immense shock waves rippling through the gas. The gas that passed through these shock fronts was compressed and heated to even more extreme temperatures. Today, we can still see the faint, arc-like borders of these ancient tsunamis as subtle, extended hotspots in the temperature map. They are the fossilized heat signatures of the collisions that built the Coma cluster. But mergers are not the only source of heat. Look toward the central giant galaxies, and you will often find localized, intense hotspots that coincide with the locations of active galactic nuclei. When a supermassive black hole feeds, it doesn't just emit light, it injects colossal amounts of mechanical energy into its surroundings. Powerful jets can drill through the intracluster-medium, creating cavities or bubbles of very hot, rarefied gas. The rims of these bubbles are often sharply defined regions of increased temperature where the jet's energy has been deposited. These AGN-driven hotspots are evidence of a relatively recent outburst, a blast of energy that has locally reheated the gas and temporarily disrupted the cluster's atmosphere. On the other side of the spectrum are the puzzling cold fronts we discussed earlier, which show up as sharp, coherent edges where the temperature drops dramatically. But beyond these well-defined fronts, there are also more diffuse cold spots, regions that are inexplicably cooler than the models predict. These could be the lingering, undisturbed cores of gas from galaxies that fell into the cluster long ago, pockets that have somehow resisted being fully mixed and heated by the chaotic environment. Or they might point to something more fundamental about the physics of the gas itself. This is where the anomalies challenge our basic assumptions. The presence of such sharp temperature gradients and long-lived cold spots suggests that heat is not flowing through the intracluster medium as easily as we once thought. In a perfectly conducting gas, heat would rush from hot areas to cold ones, smoothing out all differences almost instantly. The fact that these spots persist for billions of years implies that something is inhibiting this conduction. The tangled magnetic fields that thread the plasma are the prime suspect, acting as a blanket that prevents efficient heat flow. Similarly, the viscosity or internal friction of the gas might be much lower than expected, allowing hot and cold regions to slide past each other without mixing. These temperature map anomalies, therefore, are more than just a record of violence. They are a live diagnostic of the cluster's fundamental properties. By studying their shape, size, and longevity, astronomers can estimate the strength of the magnetic fields and measure the effective viscosity of the plasma. They can distinguish between heat from a billion-year-old merger and heat from a black hole outburst 50 million years ago. Each hot and cold spot is a piece in a four-dimensional puzzle, allowing us to reconstruct not just what happened to the coma cluster, but how its very atmosphere behaves on the largest scales. The weather in this galactic metropolis is stormy, complex, and preserved in exquisite detail. If we know how to read the map, the temperature map of the coma cluster reveals a history written in heat, but at the very center of that map, within the ghostly giant NGC 4889, lies an object that defies the timeline of the universe itself. This is the overmassive black hole, a gravitational monster of almost incomprehensible scale. With a mass estimated at 21 billion times that of our Sun, it ranks among the most massive black holes ever discovered. Its sheer size is not the only puzzle. It is the timing of its growth that creates a profound cosmic contradiction. For a black hole to reach such a staggering mass, it would need to feast voraciously on gas and stars for billions of years. Yet, the universe was only a few billion years old when this behemoth must have achieved most of its growth. How did it find so much fuel so quickly in the sparse early cosmos? This challenges the standard models of black hole formation, which struggle to explain how such titans could assemble in what was, cosmically speaking, a very short amount of time. The leading theory suggests it did not grow slowly from a single seed, but through a frenzy of mergers in the dense, primordial environment that would become the coma cluster. In the chaotic early universe, the progenitors of NGC 4889 were likely multiple large galaxies, each with its own substantial black hole at its core. As these galaxies collided and merged, their central black holes would have spiraled together and combined, creating a single, ever larger monster through a series of cosmic cannibalism events. This process could have fed the black hole far more efficiently than any steady diet of gas, but this explanation only deepens another mystery. Today, this colossal black hole is quiescent or dormant. It is not actively feeding, and it shows no signs of the brilliant, energetic outbursts typical of an active galactic nucleus. It sits quietly at the heart of its diffuse galaxy, a sleeping giant. This quietude is the second part of the enigma. Why did the feast stop? The answer may lie in the very environment that helped create it. The same violent merger history that built the black hole likely also heated and disrupted the gas reservoirs in and around the galaxy. Furthermore, as the coma cluster matured, the intense ram pressure and galaxy harassment in its core would have stripped away the cool gas needed to fuel further growth. The black hole may have essentially eaten itself out of a home, consuming or dispersing all available fuel within its reach. Now, with nothing left to fall in, it rests. This presents a critical test for our understanding of black hole galaxy co-evolution. For years, astronomers have noted a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. The two seem to grow in lockstep, suggesting their fates are intertwined. NGC 4889's overmassive black hole, residing in a galaxy whose outer regions are strangely faint and star-poor, disrupts this neat relationship. It implies that in the extreme environment of a cluster core, the black hole and its host galaxy can have very different histories. The black hole might have grown rapidly through mergers, while the galaxy's stars were being stripped away by cluster processes. This forces us to ask, does the black hole dictate the galaxy's fate, or is the galaxy's fate imposed upon the black hole? In the violent metropolis of the coma cluster, it seems the environment itself can rewrite the rules of this cosmic partnership, creating relics where the heart is far more massive than the body it resides within. The formation of a galaxy is not always a story that begins in the primordial dark. Sometimes it starts with a catastrophe. Scattered throughout the debris fields of the coma cluster, where galaxies have collided and been torn apart, astronomers are hunting for a special class of objects, tidal dwarf galaxy candidates. These are not galaxies born from the collapse of ancient gas clouds, but rather they are new islands of stars being assembled from the wreckage of old ones. When two massive galaxies swing past each other in a close encounter, their mutual gravitational pull can stretch out long, luminous rivers of stars' gas and dust. Within these tidal tails, denser knots of material can collapse under their own gravity, igniting star formation and potentially coalescing into a small, bound galaxy. It is a phoenix rising from the ashes of a galactic disaster. The challenge in a place like Coma is spotting these faint newborns against the blinding backdrop of 1,000 brighter galaxies. A true tidal dwarf would have distinct signatures. It would be relatively small and faint, yet surprisingly rich in metals, the heavy elements forged in the hearts of the stars from the parent galaxies. This metal-rich nature is the key clue, a chemical fingerprint proving its material was recycled from older stellar populations, not pristine gas from the early universe. Finding and confirming such objects in Coma would force a dramatic rethink of galaxy formation in the densest environments. We have long viewed clusters as places where galaxies are destroyed and quenched, their star formation snuffed out. The confirmed existence of tidal dwarfs would prove that the same violent interactions that tear galaxies down can also, paradoxically, build new ones. It would reveal a continuous cycle of destruction and rebirth operating within the chaotic metropolis. Each candidate represents a test of our understanding. Are we seeing true, self-gravitating galaxies that will survive for billions of years? Or are they just temporary, glowing clumps destined to dissolve back into the intracluster light? If they are real, they add an entirely new chapter to the life story of a cluster, one where even in death, galaxies can give birth to something new. Scattered across the X-ray map of the Coma cluster are dozens of tiny, brilliant pinpricks of light. These are not the diffuse glow of hot gas or the bright cores of giant galaxies, but sharp, isolated points of intense energy. Astronomers catalog them as unidentified point-like X-ray sources, and each one is a mystery waiting to be solved. They appear as solitary beacons in the darkness between galaxies, with no obvious optical counterpart, no visible star or galaxy at their location to explain the furious X-rays pouring out. So what are they? The possibilities are as fascinating as they are varied, each pointing to a different exotic inhabitant of the cosmic city. One strong candidate is a background quasar, a galaxy so far beyond coma that its brilliant, active core is compressed by distance into a single point of light. Its X-rays would shine right through the cluster, appearing as an unrelated celestial lighthouse in the foreground. Another possibility hits closer to home. These could be isolated neutron stars, the incredibly dense, city-sized cores left behind when massive stars explode. If such a stellar corpse is drifting through the cluster, alone and unseen, it could be accreting a thin wisp of gas from the intracluster-medium. As this gas spirals onto the neutron star's surface, it would heat to millions of degrees and flare in X-rays, creating a perfect point source. Yet another, and more tantalizing, idea is that some of these sources could be intermediate mass black holes. These are the elusive missing link between stellar mass black holes, formed from collapsing stars, and the supermassive monsters at galaxy centers. With masses ranging from a few hundred to a few 100,000 times that of our Sun, they are predicted to exist but have been incredibly difficult to find. An intermediate mass black hole wandering between galaxies in coma, pulling in gas, would shine brightly in X-rays and appear exactly as one of these unidentified points. The difficulty lies in telling these possibilities apart. Pinpointing the exact location of an X-ray source is challenging, and matching it to an incredibly faint optical object requires the most powerful telescopes and painstaking work. It is like trying to identify a specific street lamp in a photograph of a distant city taken from an airplane. The significance of solving this puzzle is immense. If they are background quasars, they become useful probes, their light subtly altered by the cluster's gravity and gas, helping us map its total mass. If they are isolated neutron stars, they offer a rare glimpse into the final stages of stellar evolution in a cluster environment, revealing a population of ancient stellar ghosts. But if even one is confirmed as an intermediate mass black hole, it would be a landmark discovery. It would prove that these objects can exist untethered from galaxies, potentially formed in the dense cores of ancient globular clusters that were later stripped away. It would open a new window into understanding how the supermassive black holes in galaxy centers might have grown, starting from these mid-sized seeds. Each unidentified point on the map is therefore a question mark with cosmic implications. They remind us that even in a well-studied metropolis like the Coma Cluster, unknown actors are still playing their parts in the shadows, their identities hidden behind a veil of high-energy light. These mysterious X-ray points exist within a far larger, invisible architecture. Woven through the superheated plasma of the Coma Cluster is a network of magnetic fields, a cosmic filament of force that shapes everything it touches. We cannot see these fields directly, but we can map their ghostly presence through the polarized radio light they leave behind. When electrons spiral along magnetic field lines, they emit radio waves with a specific orientation or polarization. By meticulously measuring this polarization from the vast radio halo and the sharp radio relic, astronomers can trace the field structure. What they reveal is not a simple, uniform blanket, but a chaotic, tangled web of magnetic filaments stretching across millions of light years. The strength and complexity of this web are staggering, posing a fundamental question about its origin. Did these fields form with the cluster itself, woven into the fabric of the universe from its earliest moments, or were they forged in the violence of its later life? One compelling theory points to the cluster's turbulent merger history. As subclusters collided, the immense shock waves and the resulting churning motions could have acted like a cosmic dynamo, stretching and amplifying weak, seed magnetic fields until they grew into the powerful network we detect today. It is a process of magnetic energy built from the kinetic energy of chaos. The alternative is a more primordial origin. Perhaps these fields were imprinted on the universe during its inflationary infancy, a fossil from a time before the first stars. The cluster then simply inherited this magnetic blueprint, preserving it within its growing gravitational well. The true answer likely lies somewhere in between, a combination of an ancient seed dramatically amplified by eons of cosmic storms. Regardless of their origin, these magnetic fields are not passive spectators. They are active players in the cluster's ecology. Their most visible role is in particle acceleration. The tangled fields act as a natural containment grid and accelerator for charged particles. When a shock wave from a merger rips through the cluster, electrons can get trapped within these magnetic filaments, bouncing back and forth and gaining tremendous speed with each pass. This process is what ultimately creates the brilliant synchrotron emission of the radio halo and relic. Without these fields, there would be no radio glow, no map of the cluster's invisible energy. But their influence runs deeper into the very thermodynamics of the hot gas. Magnetic fields can suppress the conduction of heat. In a perfectly conducting plasma, heat would flow rapidly from hot regions to cold ones, smoothing out the temperature map anomalies we discussed earlier. The fact that sharp cold fronts and patchy hot spots persist for billions of years suggests the tangled magnetic web is acting as a brilliant insulator. It wraps around structures, inhibiting the random motion of particles that carries heat, allowing different climatic zones to exist side by side in the intracluster-medium. Furthermore, these fields contribute pressure. They provide a form of non-thermal support, helping to hold the hot gas against the crushing weight of the cluster's own gravity, subtly influencing how the gas sloshes and flows. Understanding this magnetic architecture is like finally noticing the scaffolding on a building you have studied for years. It has been there all along, silently directing the flow of energy, shaping the weather, and illuminating the aftermath of violence. The coma cluster's magnetic field is its nervous system, an invisible network that connects every explosion, every collision, and every orphan star into a single dynamic entity. The ghostly light between galaxies and the tangled magnetic web are both echoes of a deeper foundational violence. To truly understand the coma cluster today, we must become cosmic detectives, reconstructing its violent past from the scattered clues it left behind. This is the puzzle of its subcluster merger history. The cluster we see is not a single, monolithic object that formed peacefully. Instead, it is the product of a brutal construction project built over billions of years from the collisions and mergers of smaller groups of galaxies known as subclusters. The evidence for this is everywhere, from the vast radio relic marking an ancient shock wave to the sloshing cold fronts in the hot gas and the peculiar alignments of galaxies. Each is a piece of forensic evidence from a different crime scene. The challenge lies in piecing together the exact sequence of events. When did these mergers happen? At what angles did the subclusters collide, and with what relative speeds? Answering these questions requires a combination of deep observation and sophisticated computer simulation. Astronomers begin by creating the most detailed three-dimensional map possible of the present-day cluster. They plot the positions and motions of thousands of galaxies, and they map the intricate temperature and density structure of the hot gas in exquisite detail. They then feed this snapshot into supercomputers and run countless simulations, rewinding time to test different merger scenarios. They ask, if a subcluster of a certain mass struck the main cluster from a specific direction 2 billion years ago, would it produce the exact pattern of disturbances we see today? It is a painstaking process of matching a digital model to cosmic reality. The disturbances are the key. For example, the specific shape and location of the giant radio relic tells scientists about the speed and geometry of a particular merger shock. The pattern of sloshing cold fronts in the central gas reveals the direction from which a smaller group plunged into the core, like ripples in a pond pointing back to where the stone entered. Even the distribution of the intracluster light, the faint glow of orphan stars, can trace the gravitational debris trails of long-digested galaxies. Getting this history right is not just an academic exercise. It is the master key that unlocks nearly every other mystery we have explored. The overmassive black hole at the center of NGC 4889 likely grew to its monstrous size through the rapid mergers of multiple galaxy cores during these events. The puzzling patchwork of heavy elements in the hot gas was stirred and deposited by the shock waves and turbulence of these collisions. The powerful radio halo is likely kept alive by the turbulent energy still sloshing from the last major merger. Even the transformation of spirals into red sequence ellipticals was accelerated and shaped by the increased density and violence during merger epochs. In essence, the subcluster merger history is the origin story for the entire chaotic metropolis. It explains why the cluster looks and behaves the way it does today. Without this violent past, Coma would be a quieter, more placid place, and its 25 unexplained phenomena would not exist. By reconstructing this timeline, we are not just looking backward. We are learning the universal rules of how all great clusters are assembled through a billion-year symphony of controlled chaos. Even the echoes of ancient violence might still whisper across the void. The final phenomenon is a speculative, ghostly signal, the possibility of light echoes from cataclysms long past. Imagine a titanic supernova exploding in a coma cluster galaxy billions of years ago, or a star being shredded by a black hole in a brilliant tidal disruption event. For a brief, furious moment, an immense flash of light would have flooded the cluster. While that initial flash raced away into the universe long ago, some of its photons might have taken a longer path. They could have struck vast, faint clouds of dust drifting in the intracluster-medium. This dust, likely the debris from countless stellar winds and past galactic collisions, would have scattered that ancient light in all directions. A tiny, almost imperceptible fraction of that scattered light could, billions of years later, finally be arriving at our telescopes. This would be a light echo, a delayed reflection of a cosmic catastrophe. Detecting such a signal is a monumental challenge. It would be an incredibly faint, diffuse glow, likely in optical or ultraviolet wavelengths, superimposed on the already complex background of the cluster's own starlight and intracluster light. It would require instruments of extraordinary sensitivity and sophisticated software to isolate this whisper from the cosmic noise. Yet the scientific reward would be nothing short of a time machine. A confirmed light echo would not just tell us that a violent event happened, it would allow us to date it with remarkable precision. By measuring the geometry of the echo, the apparent size of the expanding light shell as it illuminates different dust clouds, astronomers could calculate exactly how long ago the original explosion occurred. It would provide a direct physical timestamp for a specific moment of chaos in the cluster's history. Furthermore, by analyzing the spectrum of the echoed light, scientists could determine the nature of the cataclysm itself. Was it a specific type of supernova revealing the death throes of a massive star? Or was it the distinctive signature of a star being torn apart by a black hole, telling us about the activity of these monsters in the cluster's past? Each detected echo would be a single frame recovered from a lost cosmic film, filling in a blank in the cluster's violent biography. It would transform the intracluster medium from a simple hot plasma into a gigantic, dusty echo chamber, preserving the memory of flashes that illuminated this galactic city eons before Earth even formed. The hunt for these echoes is a search for the most ephemeral of fossils, not made of stone or bone, but of delayed light itself. A final, faint testament to the fact that in the coma cluster, even the loudest bangs never truly fade to silence. These light echoes would be whispers from a past that is still shaping the cluster's future. But what is that future? The ultimate destiny of the coma cluster is written in the interplay of two opposing cosmic forces, relentless gravity and the mysterious repulsion of dark energy. For billions of years, gravity has been the undisputed architect, pulling galaxies together, driving mergers, and building this immense metropolis. It will continue to do so. The cluster is not an island, it is part of the larger cosmic web. In the distant future, perhaps tens of billions of years from now, the coma cluster is predicted to merge with its massive neighbor, the Leo cluster. This would be a collision of titans, a final, catastrophic merger on a scale that dwarfs anything in its past. The shock waves would re-energize the intracluster-medium to unimaginable temperatures, and the radio halo would blaze with a final, furious intensity as the two giants become one. Within this new supercluster, the individual galaxies themselves face a slow transformation. The relentless processes of harassment, stripping, and cannibalism will continue until no spiral galaxies remain. Every galaxy will eventually be drawn into the gravitational well at the center, merging to form a single, monstrous elliptical galaxy of truly staggering proportions. It will be a smooth, red giant containing the combined starlight of thousands of original galaxies, orbiting a black hole of almost incomprehensible mass. The hot gas, too, will evolve. As star formation ceases everywhere and black holes run out of fuel, the furious outbursts of Higgian feedback will finally fall silent. Without this internal heating, the intracluster medium might at last begin to cool as originally predicted, but it will be a cooling without purpose. With no galaxies left to rain upon, the gas will simply grow colder and more diffuse, spreading out into a thin, dark sea surrounding the lone central galaxy. Yet, this gravitational destiny may not be the final chapter. On the largest scales, dark energy is causing the expansion of the universe to accelerate. As time stretches on, this repulsive force will begin to dominate the cosmic story. While gravity binds the coma cluster tightly, dark energy works on the spaces between clusters. In the far, far future, as the universe expands at an ever-increasing rate, the connections to other clusters and superclusters will be severed. The light from galaxies outside the cluster will redshift into invisibility, and the cosmic web will fray. The merged supercluster, containing the remnants of coma, will become an island universe in truth, floating in an ever-darkening, ever more empty void. Its own member stars will age, burning through their fuel. One by one, stars will die, some leaving behind white dwarfs that cool to black, others collapsing into neutron stars or black holes. The giant central galaxy will fade, its red stars dimming over trillions of years. The final state, in the almost eternal future, may be a solitary, supermassive black hole adrift in a vast, cold, and nearly empty expanse of dark matter and diluted particles, a silent monument to the chaotic, vibrant metropolis that once was. The 25 unexplained phenomena we have explored are not just puzzles. They are the active, dynamic processes that are steering the coma cluster along this immense journey from a bustling city of light to a quiet, dark relic. Every missing baryon, every shock wave, and every transformed galaxy is a step on this billion-year path. By studying them now, we are reading the opening chapters of a story whose ending is written in the fundamental forces of the cosmos itself. From ghostly dark matter halos to colossal radio relics, each of these 25 phenomena presents a unique challenge to our understanding. The coma cluster is far more than a distant collection of galaxies. It is a living, breathing cosmic laboratory where the fundamental laws of physics are tested under the most extreme conditions imaginable. Every unexplained detail, from the missing baryons to the overmassive black hole, acts as a critical piece of evidence in the grand investigation of our universe. These mysteries are not dead ends, they are the very engines of scientific discovery, each one forcing astronomers to question assumptions, refine theories, and build ever more powerful instruments to peer deeper into the chaos. The cluster's violent weather, its hidden magnetic architecture, and its fossilized light echoes all tell a unified story of a universe built through relentless dynamic change. So, as we look up at the night sky, remember that within the faint smudge of distant starlight lies a metropolis of 1,000 galaxies, each holding secrets that continue to redefine reality itself. Which of these 25 mind-bending phenomena fascinates you the most? Let us know in the comments below, and subscribe to join us as we continue our deep dives into the greatest mysteries of space.